flows over here, because it's fairly nicely streamlined, we don't lose much energy in the form of heat, and therefore we can say mechanical energy is conserved. So take this thing, in there, so it's pointing upstream. This is known as a pitot tube. Out there, pointing upstream. Get that thing out of the way. In the middle, that's good, yeah. Just give it a chance. See the levels coming up a little bit higher.
Yeah.
That is a measure of the kinetic energy. And that is V squared over 2G. That is what's known as the velocity head. And that is therefore known as the energy line. So it's a complete measure of the energy. The energy here is that amount of potential energy and a little bit of kinetic energy. Right, we just hang on to it, we just move a little bit downstream. The theory says that I can draw that line across, and if we put in our pitot tube there,
The same.
it goes up to the same level, yeah?
Is that because there's a higher velocity
Yeah, it's
at
going
that
faster.
point, but then
it's
it
going
transferred
faster,
into yeah.
And there's so we're saying energy is conserved, but we also know there's a particular place, YC, which is the critical depth, and at YC, this is big H here. At YC is 2/3 of H, and VC squared over 2G is 1/3 of H. So you're just looking at it, YC is probably round about where I've got it, 2/3, 1/3.
Yeah.
And from that, we generate that formula. The theoretical formula is entirely based on that. That's
Okay.
complete theory. So we got our theoretical equation, Q equals some constant times big H to the 1.5.
Which letter is this for? What's this stand for?
What?
What this one stands for?
Oh, just all the 2/3, 2/3 to 3, 2/3 to 3 upon 2, root G, B, etc. Right, there are two corrections we need to apply. Correction 1, how do you measure big H in a river?
Using a pitot tube.
What would happen to a pitot tube in a river?
Stuff will get blocked up.
It gets blocked up in about 10 seconds. So we can't really measure big H, but we can measure little h easily. And so we need a correction 1 is CV is H over H to the 3 upon 2. In other words, we're replacing big H with little h. That will always be greater than 1. And because it's just a function of geometry, you've got a little graph that allows you to look it up.
That's what.
So it's no problem with the theory, that is just a geometrical thing that allows you to go from big H to little h and replace it. That's number 1. The second correction is a CD value, and a CD value is known as the discharge coefficient, and that is telling you that actually energy is never conserved. That takes into account the energy lost. And it's always round about 0.98, that sort of thing, because energy is pretty much conserved with just a small loss. Now, although they don't have to do it, they've actually, CD is just a number that comes from lots of experiments. But what they've done with this particular British standard is they've tried to give it a bit of a theoretical thing. That's turbulent flow. Look at it on the side, that's laminar flow. There's a thin layer of water on the side that's going much slower. You see it? And so on here, you've got a layer on the bottom that's moving much slower as laminar flow, and a layer on the side.
You've got different flow in same channel.
Well, you've always got this stuff gets blocked up. You've got a turbulent flow which looks like that. So if somebody asks you what type of flow is this, it's a turbulent flow. But on the boundaries, there's always a thin layer of laminar flow, which is why it's such a complicated topic, really, because it's actually fairly difficult. And what the nature of CD is, you can probably see it, it's saying rather than being that wide, it's B minus a little bit, and rather than being that H, it's H minus a little bit. And so you're calculating your value of CD. You don't really need that. They could have just given us a table of numbers or a formula. But they're trying to make it look more related to the theory.